Hi class, welcome back. Today we're going to discuss increasing and decreasing functions and the first derivative test. Now, the first derivative test happens to be a very important concept in our class, so let's put an extra effort here. So we'll be referring to the first derivative test a few times throughout the semester, and it's a very efficient way to find a relative max and relative min. So what are the objectives? To determine intervals on which the function is increasing or decreasing, and then be able to apply the first derivative test to find relative extrema of a function. So before we can get to the first derivative test, we sort of gotta build out some of the techniques and skills to be able to apply the first derivative test. So we'll start with first by finding how the intervals for which the function is increasing, decreasing. So let's first learn how to derive these intervals, and this will help us later on to find the relative extrema. Okay, so first of all, what is a function where a function f is increasing on an interval when for 2x values where x1 is smaller than x2, this will imply that f of x1 is smaller than f of x2, and vice versa. If a function f is decreasing on an interval when for any two values x1 and x2 where x1 is smaller than x2, but in this case now f of x1 is greater than f of 2. So it's better actually to see it on a picture though. So a quick reminder, when we read a graph regarding increasing, decreasing, we always go from left to right. So we're going in this direction. Let me put a note there, sort of that direction, right? So because we're saying we're going from small x value, from the small x value to a greater x value, sort of what's going on here, from x1 small number to a greater value of x. So that's how we are going, right? So we want to keep that order. So the function is going to be decreasing if as x is getting bigger, the value of the function is getting smaller, right? So the function is decreasing. And if we jump on this side, the function x is getting bigger, and now the function is getting big as well. So now in that case, the function is increasing. So pretty much as if you go from left to right and the function is making you go down, that's decreasing. If the function is making you go up, then the function is increasing. Now again, it's from left to right. Now if the function happens to be horizontal, then that means the function is constant. It doesn't change, right? It's still the same value. Now this is actually very important for us. We want to be able to find these intervals where the function is decreasing, increasing, and is constant. So the question is, the million-dollar question is, how do we relate this to calculus? Well, we already know that whenever you have a decreasing function, we know that the slope is negative. So therefore, the derivative is negative. So from this interval where the function is decreasing, the derivative is negative. When the function is increasing, the slope is positive. So slope equals derivative, so derivative in this case is positive. When the slope, when the function is constant, then the slope is 0, and so the derivative is 0. So increasing, constant, increasing, derivative is 0. Derivative is negative, derivative is 0, derivative is positive. All right, so for the next part, as shown in theorem 3.5 below, we can define a positive derivative, which will imply a function is increasing, a negative derivative, which will imply the function is decreasing, a zero derivative, an entire interval implies that the function is constant. So here we have our theorem that will sort of generalize what we have discussed, right? So if the function f is continuous on a closed interval a to b, and obviously differentiable on an open interval a to b. If the derivative is greater than 0 for all x within this open interval, then we can say f is increasing on this closed interval a to b. If the derivative is negative for all x in between a and b, then f is decreasing between a and b. And if the derivative is 0, then for all x between a and b, then f is constant between the closed interval a to b. Now, do you see how we relate? This is very important. The relationship between recognizing the sign of the derivative tells you something about the behavior of the function. That's what we're trying to get here. How can we learn something about the behavior of the function? By looking at the derivative. That's the name of the game, right? That's the name of the game. So we want to know whether the function is increasing, decreasing, or constant. And for that, we don't need to graph anymore. We just have to find the derivative. So that's how we can relate this to what we're doing in this course. So we can rely on the derivative of the function. So again, without graphing this function, we're going to be able to determine the intervals for which the function is increasing or decreasing, again without graphing. And obviously we're going to confirm it here because I have a picture here for us to confirm it, but we're now relying on the picture. In this case, we can always do it by using calculus. So obviously the function is continuous and differentiable because it is a polynomial. So therefore we are able to start by finding what we're going to do. The way we're going to do it is we're going to find first sort of like breaking points. We're going to find whenever the derivative is 0, and then we'll sort of describe a strategy for the future. So we're going to first find when the derivative is 0. So we're going to set this equal to 0. Find where the derivative is 0, so we set that equal to 0, and solve for x. By factoring 3x into from those two terms, you're left with x minus 1. By the zero factor property, this suggests that x has to equal 0 or x minus 1 has to equal 0. And then, so that gives us what we call the critical numbers, right? This is a set of critical numbers. Then what we're going to do here is we're going to create a number line. So we're going to create this number line. So draw a number line. Those are the two arrows, and these represent, the number line represents the x values. So we're gonna place the one of the critical numbers, which is 0, and the other critical number, which is 1. Now you gotta put them in order. So small number, bigger number, right? And then what you're gonna see here is that by making this number line, we have created 3 regions. In other words, 3 intervals. That interval, and that interval, and that interval. Now, if you guys notice, there's no other number in the number line where the derivative is 0, right? Because if there were, then we would have found it in this process. So we are guaranteed here that there's no other derivative. There's no other locations where the derivative is 0. So, but now what we're gonna do here is. So my recommendation is once you have the 3 regions, I want you to choose any number on the left side of 0 and any number between 0 and the other critical number 1. So I'm gonna pick 1/2, and then another number on the right side of the other critical number, which is in this case I'm gonna choose 2. So those numbers can be random. We tend to pick those numbers randomly, but in mind that we try to use numbers that are practical to calculate later on, so that we can use this in the calculation, and it's not very hard for us to use them. So we try to think about numbers that are easy to compute, right? So -1 is an easy number, 2 is an easy number. Number between 0 and 1, they're all fractions, so I picked the easiest one, 1/2. But it could be any number. So the next part is what I do is I set I put on the value. I write the x value here, and I write the derivative function here. And what I'm trying to do here is I'm gonna express the value of the derivative in this row. So I'm gonna put in x equals 0. X equals 0. The derivative value is 0. How do we know that? Because that was a critical number, right? At x equals 0, if you go backwards, your derivative is 0. at x equals 1, same argument, the derivative is 0. Do I need to make this a little more obvious here? F prime of x, right? F prime of x. F prime of x is 0. So I'm going to put a 0 there. I'm going to put a 0, so that's the value of the derivative. The name of the game here that we're trying to do is fill in the what is in each of the regions. So can you figure out what is the sign of the derivative in each of those cases? And it's actually pretty straightforward to do. What we're going to do is we're going to test a few numbers. That's the number we're going to test, that's the number we're going to test, and that's the number we're going to test. And where are we going to test them? We're going to test them in the derivative. So we're going to take the derivative function, and the derivative function happens to be right here, right? This is your derivative. Now you have the option of using this one, or that one. Please choose the one that is factor, because it will make everything much easier. Now all we're looking for is whether the derivative is positive or the derivative is negative, because as you guys will see here, if the derivative is positive, it means that the function, I'm going to write myself a note over here, the function is increasing, right? So all we care, this is the beauty of this problem, is all we care about is the sign of the derivative, not the number, just the sign. And I know that that's sometimes something the students will fight. They want to find out what is the exact number of f prime, and you can if you choose to. It's just you're going to be working harder than everyone else, right? We just want to be practical. So what we're going to do is we're going to take the derivative function, which is right here. Let me sort of write it up here. F prime of x is equal to 3 times x minus 1. And what we're going to do here is we're going to take and we're going to replace x with -1. So plug in -1 for x, that gives you -1 in there, plug in -1 there, and again all we care is whether this is positive or negative. Well, 3 is a positive, -1 is a negative, so positive times negative gives you negative. So that's my first negative right here. I'm going to multiply it, followed by multiplication of -1 minus 1, which is -2, but I don't care. It's just I know that it's negative. And what we're going to do here is, because multiplication, remember that negative times a negative gives you a positive. So you see here, we didn't actually have to compute or multiply the numbers. All we have to do is multiply the signs. And that way, that's how we got the positive. Now, it only works, right? This way is a better approach because, but only because we already have it in the factor form. That's why we are motivated to factor the derivative a lot of the times. Let's try this again. Now let's plug in 1/2, right, into the derivative, right? So it's important. You're plugging into the derivative. So plug in 1/2, 1/2, 1/2. That's 1/2 times 3 is positive. 1/2 minus 1 is negative. So positive and then negative, right? Positive times negative gives you negative. So it's negative between here, right? And this 1/2 represents any number between 0 and 1. So we don't care which one you plug in. Every number you plug that you plug in here into the derivative will give you always a negative number. And then so we'll try now positive 2 into the derivative. 3 times the positive, 2 minus 1. So this will give you a positive, this will give you a positive, and positive times positive gives you positive. So positive, positive, positive. So we already have sort of the signs of the derivative. And now what I like to do is sort of drive myself a note here, a picture. Here's your function. The function must be increasing because the derivative is positive. The function must be constant because the derivative is 0. The function must be decreasing because the derivative is negative. The function must be constant because the derivative is 0. The function must be increasing because the derivative is positive. And so when they ask us, can we figure out for the open interval for which the function is increasing, I figure out that is any place from -infinity all the way to 0, right? Again, you refer to the x values. So from -infinity to the 0, you're gonna be increasing. Between 0 and 1, you're gonna be decreasing, and from 1 to infinity, you'll be increasing. And so to write the conclusion of this, we're going to say by theorem 3.5, f is increasing on the interval negative infinity, 0, and 1 to infinity, and we can observe that it is decreasing on the interval from 0 to 1. As we can see in the figure, we can see the picture, it's increasing from negative infinity to 0, right? It's increasing, and then from 0 to 1 is decreasing, and then from 1 to infinity the function is increasing, and so that's how we find this intervals, right? Again, so this is very helpful because this is gonna help us now figure out relative max and relative min. So here are some guidelines that we can use to help us find this interval. So, and it's sort of what I done in the top. We first check that the function is continuous on the open interval, and then find the open interval on which the f is increasing, decreasing by following the following steps. Locate the critical numbers of f between a and b, and use these numbers to determine the test interval. Determine the sign of the derivative on one test values on each of the intervals, and then use theorem 3.5 to determine whether f is increasing or decreasing on each of the intervals. Now I want to make two remarks here. First, if you guys notice, it says locate the critical numbers. Now in this example, I only located one case of critical numbers, right? Because remember that the derivative, the f will have critical numbers whenever the derivative is 0, but also when the derivative is undefined. But in this case, it was not needed because we know that this derivative is a polynomial, and polynomials are always defined. So we didn't have to use it, but we have to consider. So now in the future, we're always going to consider this as well when we're looking for critical numbers, and we have an example like that in a second here. All right, so now we're gonna define a few more terms, right? So we want to define what does it mean to be strictly monotonic. Now the word mono comes from one, right? So so monotonic means only one direction, right? So a function is strictly monotonic, meaning it's always going to be increasing or decreasing, right? Either one on the entire interval, if it's always increasing, right? So if it's always increasing for every single value of x, then it's strictly monotonic. If it is always decreasing, let's say this is it, then this is strictly monotonic because it's always decreasing for every value of x. So meaning that there's not gonna be something like this, right, where you change direction from increasing to decreasing, or from constant. So monotonic, one direction, right? There's no turnarounds and there's no flat regions, because if you guys notice, we also have that a function is not monotonic, it's not strictly monotonic if there is a case where the function is increasing, but then it becomes on an interval, it becomes constant and then it starts increasing again. So that's not monotonic. That's not strictly monotonic. All right. So there you go. So we already discussed increasing and decreasing intervals. We're going to continue with this process. We're going to be using this process over and over again when we use it for the first derivative test. So let's explore the concept of the first derivative test. So let's look at this graph, right? Our goal is to find relative max and relative min. So if I zoom in here real quick, what does it mean to be relative max? Remember that we said last time a relative max happens when you have a hill, right? That right there is your relative max. Or whenever you have a valley, that is the minimum value relative to its surrounding. So relative max is it's a maximum value relative to its surrounding. So we have a hill, right? Hill versus valley, right? Now, if you notice, if we relate this to what we just discovered, what do we know about this? Well, we know that the function is increasing followed by a horizontal, followed by decreasing, or followed by a critical number, right? So increasing, followed by a critical number, followed by decreasing. So if you follow that order, if you have increasing, critical number, decreasing, then that's going to tell you, hey, you just found a relative max. Versus if you now switch the order and you say decreasing, followed by a critical number, followed by increasing, then what you have found is a relative min, right? Now, how do we translate this to what we were doing before? Well, remember that f is increasing when f prime is positive. F is decreasing when f prime is negative. And then f is increasing when f prime is positive. So we don't actually, so what we need to know, what we need to do is pretty much know about the derivative, whether it's positive or negative, and that will help us determine whether we have relative max or relative min. So let me erase this real quick here, and maybe let's jump into the other problem that we already had we did before in the beginning, and maybe we can make that simple conclusion by looking at what we already have. So here we go. So this problem right here. So by looking at this, we can actually now make the conclusion. They say, hey, look at this. So we have increasing, constant, decreasing. So here we just learned that there is a relative max here at x equals 0. At x equals 0, you have a relative max. Well, what about this one? We just learned that there is a relative min there because you're decreasing followed by constant and then increasing. You have a relative max at x equals 1. So you see, we already had all the tools. All we have to do is just add a concept to the end, and that give us enough information to make that conclusion. So what we're going to be doing here is sort of the same thing that we did before. We're going to find the critical numbers. Now, critical numbers could be whenever the derivative is 0 or undefined. We haven't discussed that much, but I want to keep reminding you guys that it's not just when the derivative is 0, but it's also when the derivative is undefined. And we'll have an example like that, I promise. So the derivative here is 0, and then once you find those out, then you test this region, test this region, test this region. Where? In the derivative, right? In the derivative. Once you figure out these values, these sign values, then you can determine whether the function is increasing, decreasing, increasing, right? And then will tell us whether we have a relative. In this case, we have a relative max and then relative min. All right. And that's what this is saying here. The theorem 3.6 is pretty much saying that. So let's jump in to one problem, and then we'll make and then we'll talk about that definition again. This theorem again. So here we go. Find the relative extrema. So now the question is find the relative extrema, not just the increasing. Find the relative extrema of the function f of x equals 1/2 x minus sin of x in the interval 0 to 2 pi. So we have a restriction where we're looking at this. Now we also have to check that f is continuous on the open interval and differentiable in that interval, right? So as the derivative of f is determined by the critical numbers of f, and so what we're going to do first is we're going to take the function and do the derivative of it. So the derivative of f of x, well, the derivative 1/2 x is 1/2. The derivative sine of x is cosine of x, followed by the minus in front of it. So here's your derivative. Now you got to find the critical numbers, right? The critical numbers are found whenever the derivative is 0 or when the derivative is undefined. Now in this case, because this is a constant and this is a continuous function, this will always be defined. So there is no critical numbers found from here, right? There will be no critical number. So but we still checked, right? That's good. We still checked. So now we're gonna find whenever the derivative is 0 by setting the derivative equal to 0 and solving for x. So set it equal to 0, solve for x by adding cosine on both sides of the equation. That gives you cosine equals 1/2. The cosine of 1/2, ask yourself what angle, right? You're looking for x, what angle when you take the cosine of it will give you 1/2. Well, you can look at the unit circle, and then you can think about that would be whenever the angle is pi thirds or 5 pi over 3 when we're within 0 to 2 pi. So those are the two critical numbers. What's next? My suggestion is to make the number line again, right? Separate the number line using these two numbers, so it'll be pi over 3 and 5 pi over 3. Now in this example, you should try to restrict yourself within 0 and 2 pi. So I'm going to restrict myself between 0 and 2 pi. That way I can choose numbers that are within the interval that I'm looking at. Now, why is this important? The reason is because sine functions and cosine functions are periodic functions, and so things you could have more critical numbers beyond 0 and 2 pi. So you could you can get misinformation by not doing it, by doing beyond that, because you're gonna get more critical numbers. So here we just want to stay within those two. So restrict that within those two. All right, I think that makes it clear. So let's try. We have pi over 3, 5 pi over 3, 0, and 2 pi. Then choose numbers to test that are between 0 and pi over 3, between pi over 3 and 5 pi over 3, and pi over 3 and 2 pi. Now at some point I could have chosen pi. I don't know why I didn't, but anyways, I could have. That would have been an easier number to choose, right, to work with. So you always want to choose. You want to pick numbers that are easy to work with, because we're gonna take the cosine of it. So we're gonna have to test them. So I'm gonna test this number, and this number. All right. Here's where you're gonna test them. You're gonna test them in the derivative. Now it's important for us to make a note here that if pi over 3, when x equals pi over 3, the derivative is 0, right? It's just good enough for us to actually put that note there, so you guys can remember what's going on. Please put like a 0 there and 0 there, right? We're trying to fill in this row. All right. So test pi over 4. Plug in pi over 4 here. Pi over 4, 1/2 minus cosine of pi over 4. Cosine of pi over 4 is the square root of 2 over 2. So 1 minus the square root of 2 over 2. This is bigger than 1, so when you do this mathematically, this will be a negative number, so that's less than 0. Try now pi over 2. 1/2 minus cosine pi over 2. Cosine pi over 2 is 0. So 1 minus 0 is 1/2. 1/2 is greater than 0. So there you go. The next one is 7 pi over 4. So plug in 7 pi over 4 for cosine. Cosine of 7 pi over 4, that would be positive square root of 2 over 2. So we have 1 minus square root of 2 over 2, which is also a negative number. So we figure out that this is negative right here in this region. This region is positive, and this region is negative. So now I'm going to make a picture for myself. So I'm going to draw my f of x, and I'm going to say because the derivative is negative, function is decreasing. Because the derivative is 0, function is constant. Because the derivative is positive, function is increasing. Because the derivative is 0, function is constant. And because the derivative is negative, the function is decreasing. So we can clearly see that we have found a relative min at x equals pi over 3, and a relative max at x equals 5 pi over 3. Now what we need to do here is we still gotta find we actually do have to find the relative extrema. That means we actually have to find the y component. We know where it happens, we know where the extrema happens, the relative extrema happens, but we don't know what the actual relative extrema is. For that we have to actually find the y value. So how do we find the y value? Once you know the x value, plug it into the function, and so that's what I did up here. So I plugged in 5 pi over 3, and and the 5 pi over 3, we plugged it into the equation. 5 pi over 3 minus sine pi 5 pi over 3, and that gave me, you can put this in the calculator, that gave me 3.48. The next one, I plugged in pi over 3 into the function, 1/2 times pi over 3 minus sine pi over 3. That gave me a negative number, and that's the negative value that we're getting here. So this is the minimum, this is the relative min, this is the relative max. And maybe I should put be a little more careful here. Relative, right? And there you go, right? We found our relative extrema. I hope you guys find that helpful. This is very my suggestion is work on the organization. I think the problems are doable, but organization is key. And if you guys like my style, then you guys can sort of just copy and paste, copy it, and I don't mind that. All right. So moving on to the next problem, practice 3. Applying the first derivative test, find the relative extrema of this function. Well, we'll begin by recognizing that the function is continuous on the entire real number line, and because it's defined everywhere. And by applying the first derivative test, you can conclude that f has some relative extrema around. So let's jump in here. So here's the function. First thing is first, let's find the critical numbers. So first, find the derivative. We have to use chain rule. So we'll multiply the power 2/3 to the original function, and then subtract 1, and then multiply by derivative of the inside. And that's what we did. 2/3 times the inside minus 1 gives us negative 1/3 times derivative of the inside is 2x. So we'll simplify this first. 2x times 2 is 4x. And then because this has negative power, we're going to move that to the denominator. So that will be 3 times x squared minus 4 to the power of 1/3. Now again, since we're looking for the critical numbers, we're going to find the case where when the derivative is 0, that will be a smooth hill or a smooth valley, or whenever the derivative is undefined, which will be a corner a hill or a corner valley, right? Now in this case, this is the first example that we've done today where we actually have this one here. So I always write it out, but this is the first time we actually have something to work with. So the suggestion here that I tell my students is make sure that if you have that case where you have a rational a fraction, a polynomial, a division of two polynomials, sorry, not two polynomials, but a function over a function, sorry, then to find whenever this is the case will happen, the derivative will be 0 whenever the numerator is 0, right? That's sort of the technique that we use, because the only way this is going to be 0 is whenever the numerator is 0. It doesn't depend on the bottom. Now to find whenever this whole thing is undefined, this will happen whenever the denominator is 0. So I sort of have this sort of structure in my mind. I look for whenever the numerator is 0, and I look for when the denominator is 0, and that gives me the two critical numbers that I need. I think that's kind of neat that it works out that way, and I think we could take advantage of this. So when the numerator is 0, then we set that equal to 0 and solve for x. That would happen whenever x equals 0. So we found the first critical number. Let's try the second case. The second case happens when the denominator is 0. So we set that equal to 0 and solve for x by dividing both sides by 3, and then by taking the third power on both sides of the equation, and then remove that power. And now we have x squared minus 4 x equal to 0 to the third, which is 0. And then add 4, and then take the square root of 4 on both sides, gives you plus or minus 2. So the other critical number is plus or minus 2. Now you have to check that these two numbers are they are within the domain of the function, and they are, right? We have to check please check that your critical numbers are in the domain of the original function. Okay. All right, so sometimes we just don't do it because most of the time it works out, but we just have to keep that in mind, right? You should always check it just to be sure. All right, so next part is to make the number line. So here's our number line. I'm going to use 0, -2, and 2. So I have to put them in order. Here's my number line. Here are my x values. -2 followed by 0 followed by 2. And then I'll fill in the blank. I'm going to pick a number here, pick a number from there, pick a number from there, pick a number from there. Now, I know I'm going to have to fill out my derivative information, and I'm only looking for signs. I know that at -2, the derivative is undefined. So I'm going to write myself undefined there. I know that when x equals 0, the derivative is 0, because that's how we found it. And when x equals 2, the derivative is undefined. By making that little note to myself, that will keep me on check later on. Then I check -3, -1, 1, and 3 in the derivative, and that's what we're gonna do next. We're gonna plug in -3 for x. This again, all we're looking is for whether this is positive or negative. So positive times negative is negative. On the bottom part, we're gonna have -3 to the second. That will be a positive 9. 9 minus 4 is 5. 5 to the 1/3 is gonna be still positive. Positive times positive 3 will still be positive. So this will be positive. Negative over positive is negative. Now I'll try -1. -1 times 4, that's going to be a negative number. -1 squared is going to be 1. 1 minus 4 is -3. -3 to the 1/3 is kind of like the cube root of -3. That could be negative. So negative times a positive gives you negative. So negative over negative gives you positive. And then do the same thing for the rest of them, right? You can do that in your head. So you can plug in 1 and you can plug in 3, and you're going to get negative and positive. And so I'm going to write between here, I'm just going to get negatives. Between -2 and 0, I'm going to get negative, positive. Between 0 and 2, I'm going to get negative and negative. And on the right side of 2, I'm going to get positive and positive. So I keep getting, so I'm going to get these values, right? Now I'm going to make myself a note for my function. So my function is going to be decreasing because my derivative is negative. It's going to be a corner, right? It's a corner because the derivative is undefined. The function is going to be increasing because the derivative is positive. It's going to be constant because the derivative is 0. The function is going to be decreasing because the derivative is negative, and the function is going to be has a corner because the derivative is undefined, and the function is increasing because the derivative is positive. And so now that gives me enough information to make this conclusion, right? So what do we have? We're looking for relative max and relative min. So this suggests that we have a relative min, we have a relative max, and we have a relative min. So let's now find the actual relative value of this, the relative extrema. So for the first one, I'm going to find my relative max. So what we're going to do is we're going to take negative, we're going to take x equals 0, because that's the relative max, x equals 0, and plug it into the regional function, right? Because remember that the actual value of the extrema is the value of the function, So the relative max is at x equals 0, so plugging in 0 for x, and that gives us -4 to the 2/3, which is the cube root of 16, right? Because you're going to square -4 and then take the cube root. So that gives you the relative max. The relative min is found by plugging -2 and then also plugging 2 into the regional function. And because this is being squared, it's not going to make a difference. They're both going to be the same thing. So 4 minus 4 is 0. 0 to any power is 0. So the relative min is 0. All right. So hope this is helpful. Please practice this. Try these problems on your own after watching this video. Try to work on your organization here. You are required to show your work when you guys are doing these problems, right? I want to see everything on this problem. So sort of what we have here. Now on this side, sometimes it's just easier for us to use a calculator. and plug in the numbers from your table like that, right? So that's sort of flexible from my end. I allow you guys to use the calculator to just plug in those numbers and figure out those signs, okay? But I want to see everything, how you get all that work there, right? This is we can think about this as very basic, but maybe you should try this at first without the calculator, and maybe double check it with your calculator just to make sure that you're doing this right. All right, I hope this is helpful, and I'll see you next time.